Hi and welcome back. We're looking at convergence issues for stationary iterative methods. Now the first question we're going to be asking ourselves is, if we converge with one of those methods, with these matrix split methods, do we actually converge to the solution we're after? So we're solving ax equal to b, do we converge to x? Now what does convergence really mean? It means that if we keep on going with this iteration and k increases, in other words, k goes to infinity, then xk plus 1 and xk, both of them, will converge to some vector which I called x star. Naturally, if this is the case, if we have convergence, xk plus 1 and xk will get closer and closer together. And that's really what's expressed here. These limits are the same. The distance between xk and xk plus 1 in every iteration step gets closer. Now if that's the case, we can take the iteration equation, mxk plus 1 is nxk plus b, and plug in this limit value, x star. So if we do that, we get mx star is nx star plus b, or in other words, throwing nx star to the other side of the equation, we get m minus nx star is equal to b, but of course m minus n is just a. So we get ax star is equal to b. Now remember, A was a non-singular matrix, so a system Ax equal to B will only have one unique solution, and if Ax star satisfies B, then that X star must be equal to the solution that we're after. So that's really nice. With a stationary method like this, with a split method, no matter how we choose M and N, if we converge, we get the right solution. And the most important question, of course, is for which M and N do we actually converge? We saw before that if M is the identity matrix, then we may not always get convergence. So obviously there are conditions on M and therefore also on N that will tell us whether or not we get this convergence. Now when we're thinking about convergence, we typically like to look at this in terms of the error that we're making. And if we have convergence, we want the error to go to 0. And the error we indicate by ek, and that is just the difference between xk and the actual solution x. One snag in this, you may think, is, well, we don't know what ek is going to be like because we have no idea what x is. In fact, x is what we're trying to find. But it doesn't mean that we cannot understand how this error will behave. Now we have this iteration equation here, mxk plus 1 is nxk plus b. And somewhere hidden in this equation will be an expression for this error ek. And the question is, how do we derive it? We start with mxk plus 1 is nxk plus b. Now we have an equation in xk plus 1. We want it in xk plus 1 minus x, which is the error ek plus 1. And we can get this by simply subtracting m of x, m times x of this mxk plus 1. But of course then we have to add it back together at the same time. And we do it the same on the right hand side of this equation. So we have nxk, we subtract nx, we add it back up, and then we have plus b. So this is still the same equation as we had before. And now we move some of these terms around. We take xk plus 1 and x together and put m in front of it like this. We have a plus mx left. We'll move that to the right-hand side of the equation. And on the right-hand side now we have nxk minus x plus nx, which was left from before, minus mx plus b. So now we get expressions in the errors. We have ek plus 1 on this side and ek on this side. And here when we take these two terms together, we have minus m minus nx plus b. But remember that a was equal to m minus n, so this is just a. M ek plus 1 is nek minus ax plus b. Now, and this is just 0, because x is the exact solution and ax is equal to b, so it drops out. And as a result, we have a very clean and very nice equation for the error that we're making at each iteration step. Again, we don't actually know how big it is, but we know how it behaves, and that's the important thing. So MEK plus 1 is NEK. Now, I know that M is non-singular, because that's one of the conditions I have for the stationary methods. So we can multiply this on both sides by the inverse of M, and we get EK plus 1 is M inverse N times EK. This matrix here, M inverse N, we sometimes label as G, and that's called the amplification matrix. And you can probably understand why we call it that way. If we have a previous error, EK, the new error is just that EK amplified by G. So EK plus 1 is GEK. Let's think about this. We start off with an initial guess x0. So we're making, we don't know how big it is, but we're making an initial error E0. That error E0 gets amplified by G to create E1. Okay. Then we have the next error, E2, at the second iteration step, is the amplification again of E1 by G. But E1 was the amplification of E0, so we get G times E0 for E2. And so E2 really is G squared E0. And we can keep doing this until we get the general expression that the error that we're making at the kth iteration step is nothing but G to the power K, the matrix, the amplification matrix, applied K times to the initial error E0. The nice thing about this is that no matter what E0 is, if this G gradually reduces this E0 and we constantly hit it with this amplification matrix, the error will go down to 0. The question really is, what is really the mathematical condition on G that this happens? Now, the general convergence theorem, which is discussed in a supplementary video, will say that we are guaranteed that this EK will be going to 0 after we hit it all the time with this amplification matrix if the spectral radius of G is smaller than 1. Now, the spectral radius, you may remember, is the largest eigenvalue of G in absolute value. We'll prove this, but we can also look at this convergence condition in a slightly simpler way just by using matrix norms. So now we look at this iteration equation, EK is G to the power K E0, and put some norms around them. So the norm of EK will be equal to the norm of that matrix to the power K times E0. Now, here I leave what kind of norm we use completely in the open. This is for any norm. And all the manipulations that I'm going to do hold for any norm. Could be the 2 norm, it could be the 1 norm or the infinity norm, or some matrix-induced norm. It really doesn't matter. The first thing that all norms satisfy is that if I have the norm of a matrix times a vector, I can bound that from above by the norm of that matrix times the norm of the vector. So in this case, it gives us the norm of the error at the kth iteration step is bounded from above by the norm of the amplification matrix to the power K times the norm of the initial guess. And we don't know how big that is, but again, this will not matter. Now, the next thing we can do with norms is if we have the norm of a product of matrices, then that is bounded from above by the product of the norms of each of these individual matrices. Which that really means is that the norm of G to the power K is bounded from above by the norm of G to the power K. It is as if we can take that K power and pull it outside of the norm. So now again we have that the norm of EK, the error we make at the kth iteration step, is bounded from above by G to the power K times E0. Now when you look at this and you think, hey, how can I make sure that this error will go to 0 as K increases? It's clear that independent of what this is, it will happen if the norm of G itself is smaller than 1. Say it's a half. G to the power K will then be a half times a half times a half times a half times a half. It gets smaller and smaller and smaller and smaller. And independent of the size of E naught, at some point, this whole thing will go to 0. Now this gives us another way of looking at convergence. We've seen the general convergence theorem tells us that we always converge if the spectral radius of the amplification matrix is smaller than 1. But we now know that we can also converge if we can find a norm any well-defined norm for which the norm of G is smaller than 1. And sometimes that's easier to do than actually checking the spectral radius, or it's cheaper to do. And what norm we use will often depend on the application.